So this video explains how we use the periodic table to determine what charge each element has. So we've talked about the periodic table before, and that it is not just randomly put together. Scientists have determined early in the 1900s that if you put the elements together in terms of atomic weight, starting with hydrogen being approximately 1.008, and then our second element is helium, and then lithium, beryllium, and continue onward, what we actually see is considered to be trends within the families. And so when we're talking about the family groups, essentially what we are referring to is that hydrogen, lithium, sodium, potassium, rubidium, cesium, all the way down, that is considered to be a family. So any vertical line that we see are considered to be families. And the reason why they're considered families is because they do behave rather similarly. And what scientists were able to determine was that the reason why they behave differently, they behave similarly, is because of the electrons in their outer shell, which is known to us as the valence shell. So our valence shell, that is that last orbit that has electrons in it. So when we're talking about chemistry and we're talking about elements combining together or disassociating from each other in terms of types of chemical reactions, really that has to do with the valence shell and the number of electrons found in that valence shell. So as I was talking about in class, your elements are lazy. Okay, they really are. They'll do the least amount of work possible, if possible. And what they're all striving for is to be considered on our far right table here, in this last family group, starting with helium, neon, and then argon, krypton, xenon, all the way down. This column here is called our noble gases. And they're considered noble gases because they actually have a charge of 0. And the reason why they have a charge of 0 is because they have 8 electrons in their outer shell. And that to us is considered to 8 electrons in each element's outer shell is the name of the game. That makes them stable, it makes them non-reactive, and they're very happy in that state. So that actually is known to us as the octet rule. Octet relating to 8, and the rule being that every element desires to have that noble gas state, which has 8 electrons in its outer shell. Of course, the exception to this rule is helium. Okay, helium is the second element on our periodic table, and therefore that first orbit that we've talked about, that s orbit, can only contain a maximum of 2 electrons. So with the exception of helium and actually hydrogen, every other element desires to have 8 electrons in that outer shell. So just keeping that in mind, I mean, lithium and beryllium, for instance, as we're going to go through this example here, the name of the game for the elements is either to have 8 electrons in their outer shell or have that charge of 0. So whether they're taking in electrons to get the 8 electrons for their outer shell, or they're releasing electrons to get down to a state of 0, those both are considered to be what is known as our octet rule. So when we go through the columns, remember I said our family rows here, is that the elements really they're lazy. Okay, so they're going to do the easiest thing possible. So when we start with our first row with hydrogen here, hydrogen's group has 1 electron in their outer shell. And so the question to ask ourselves is, well, is it easier to find 7 more electrons to get 8 in total? Or is it just easier to give off your that last electron and have a state of 0? And so it's easier to get rid of 1 electron then gain 7. So remember, our electrons are negatively charged. So when hydrogen's family group, so hydrogen, lithium, sodium, all the way down, give away that 1 electron, they become more positive because our electrons are negatively charged. So hydrogen's family has a +1 charge. Moving across to beryllium, magnesium, calcium, and down, okay, beryllium's family group has 2 electrons in their outer shell. So again, is it easier to give away 2 electrons or to take in 6 more to get 8? It's easier to give away 2, so because we're giving away 2 negative things, which are our electrons, we're actually going to have a +2 charge. Boron's group, it's not that the transition metals found in the middle aren't important. We're just not focusing on those for the purposes of our ionic and covalent bonding. So boron's group with aluminum, gallium all the way down. This is our family group 3, so it has 3 electrons in its outer shell. Again, it's easier to lose 3 electrons than to gain 5, so because it's going to lose 3 negative things, which are the electrons, it will have a +3 charge. Carbon's group is very interesting. We have chemistry has a whole subject matter dedicated specifically really to carbon, which is called organic chemistry. And that's because carbon's family group can do two, it's easy to do both of the options available to it because carbon's family group has 4 electrons in its outer shell, so it can either lose 4 electrons or gain 4 electrons. So it's really depending on the situation. So I'm going to say plus or minus 4 electrons that for carbon's group. Nitrogen's group is family number 5, and so it has 5 electrons in its outer shell. So now, is it easier to lose 5 electrons or is it easier to gain 3? So it's easier to actually gain 3 in this situation. So because it's going to want to gain 3 negative things, it'll actually have a -3 charge to it. Oxygen's family group. This family group has 6 electrons in its outer shell, so it is easier to gain 2 electrons than to get rid of the 6. So because we're gaining 2 negative things, we're going to have a charge of -2. Fluorine's group is so close to being ionic, or sorry, not an ionic gas, a noble gas, because it actually has 7 electrons in its outer shell. So it's 1 shy away from being a noble gas. So because it has 7 electrons in its outer shell, it is very easy for it to just take in another electron to be happy with that 8, as opposed to trying to give away 7. So fluorine's group actually has, fluoride's group has has a -1 charge because it's going to want to take in that 1 electron, which is negative. And again, our noble gas family has a charge of 0. So this is why we can determine the charges of our elements, at least our metals and our nonmetals, because of how many electrons are in that outer shell, which is known to us as the valence shell.